one of the standard operations, one of the most common things that you do in algebra is cancellation. So let me write this down. So one of the basic operations of algebra is cancellation. And we can never agree, no one can actually agree whether there should be one L or two right there. I think I like one L better, but I kind of go back and forth. So you write it in your notes however you like. I don't know. See, now when I look at it like that, I'm not sure. Well, cancellation. So, oh, sorry, I sometimes get obsessive with those kind of things. So for example, though, so cancellation, if I'll write this. If 2x equals 2y, then x equals y. What we do when we see an equation like this, we immediately in our head sort of cancel out the 2, or we divide both sides of the equation by 2 and allow us to conclude that x equals y. So this is a common thing that we do whenever we're doing algebra. It's one of those basic arithmetic operations. And it turns out that such an operation holds in groups as well. So this will actually be our first theorem. So our first theorem shows that this property holds in groups. So remember, I'm going to label my theorems according to the chapter. So this first theorem here is actually theorem 4.1. It's the first theorem of chapter 4. We're in chapter 4, which is the chapter on groups. And so let's let capital G be a group. For a little while, what I'm going to do, when I write this out, I'll say let G be a group with operation star. At some point, I'm really going to delete this phrase here with operation star, but for now, we'll keep it there. So let G be a group with operation star. And then for all, call them A, B, and C in capital G. Now there's two parts to this. So part A, let's do on the left first. So if A star B equals A star C, then B equals C. This property right here is called left cancellation. And so what does that mean? You see this equation right here. It tells us that we can cancel off the A's to conclude that B equals C. There's also right cancellation. And so that's part B. If A star B equals C star B, then now we would cancel the B's off and we conclude that A equals C. So that's right cancellation. And just for fun, I'm going to do double L in the second one right there. So cancellation, cancellation. What do you think of that? Sorry, I have to amuse myself sometimes when I'm talking in front of a camera. It's sort of weird, so I don't know. Anyways, so let's prove this now. And what we'll do is we're just going to prove part A. If we can prove part A, the proof of part B is going to be essentially the same proof, just do it on the other side. So here's the idea. We start off with our assumption that A star B equals A star C. So we go like this. So let's let A prime be an inverse of little a. So we have this equation right here, and if you think about how this is going to work, and you think about how you solve an equation like this, what do? Well, technically what you do is you multiply both sides of the equation by 1/2. And so what we're going to do here, 1/2 is the inverse of 2 when you're working with multiplication. And so I'm going to multiply both sides on the left by a prime. So we can say then we have a prime star A star B equals A prime star A star C. Now, what do I need to do? Well, what I really need to do is I need to combine, or I need to have the A prime and the A cancel each other out. And the good thing is we're working in a group where the associative property holds, which means that I can slide those parentheses over to the other side. So it follows that, so it'll be a parentheses A prime star A star B equals parentheses A prime star A star C. And here, make a little note for yourself in this sentence, right? So that's by associativity. So from this now, we know that A prime star A, that's equal to the identity, which we use the symbol E for that. So now we have the equation E star B equals E star C. And then we know, because E is an identity, that E star B equals B and E star C equals C. So therefore, B equals C, and that's what we needed. All right, so that completes the proof of part A. The proof of part B is similar, so we'll just write here. I think it's worthwhile to go through that. So proof of part B is similar. And then whenever I complete a proof, I'll put a little box with a slash through it to indicate that we've ended the proof. So what we showed is that in groups, remember, the idea of a group is to generalize the familiar properties of arithmetic that we know from working with the integers, the real numbers, the rational numbers, and so on. And what we're seeing is that one of those common algebraic properties, the property of cancellation, holds in groups. Now, in most of the arithmetic that you've done previously, working with the real numbers or rationals or so on, we have commutativity, and so you can multiply on either side and it doesn't matter. Notice we have two parts of that previous theorem, a left cancellation and a right cancellation, and that's because in a group, the operation is not necessarily commutative. Now, so there's one of our common operations. Another one, solving equations. And I should be specific here, solving linear equations. Solving linear equations is another basic algebraic operation. And what I mean by that is something like this. If, I'll just give it an easy one here. If 3x equals 6, then there's exactly one solution, and that solution is x. So then x equals 2 is the only solution. So it turns out that this property also holds in groups. So this property, the ability to solve equations of the same type, so this property holds in groups also. So we'll state this as theorem 4.2. So theorem 4.2. So let's let G be a group with operation star. And then I need a couple of elements in G. Let's call them little g and little h. So, and let little g and little h be elements of capital G. Once again, we're going to have two parts to our theorem corresponding to a left-hand and a right-hand scenario. So there exists a unique little x in capital G such that, and we're going to do it G star x equals h, and then there'll be the flip side. There exists a unique, I guess I should call it something else. Let's call it y, little y in G, such that y star G equals h. Hopefully I made that clear. This is a y star, and then that's a little g there. Okay, so those are the two parts to our theorem. And let's, once again, we'll prove part A, and we'll leave part B as an exercise for you. Okay, so let's see now. What we need to do is we need to identify, right? We need to figure out who this x is going to be. Who's the appropriate x? And notice in this proof, this has two parts to it, really. There's an existence and a uniqueness. And so first, let's prove the existence portion. So part A, for the existence, well, let's see now. Who is it going to be? I need somebody so that when I put it right there, some element, so that when I plug it in for x, right, we get equality. And so hopefully it's clear if we say letting x equal G prime star h, we see that, all right, so how does this work? G star, G prime star h is equal to, use the associative property, this is G star G prime star h, and that's equal to E star h, which is equal to h, right? So inserting that element right there in place of x in our equation gives us h, right? So that shows us the the existence, and now I need to prove the uniqueness. So now what I'm going to do is say, suppose we have a couple of elements who, when plugged in for x, satisfy that equation. So suppose x and x hat in G are such that, all right, so we would have G star x equals h and G star x hat equals h. What I need to do now is show that x has to equal x hat. Well, notice now, both this piece and this piece, they're both equal to h, which means that they're equal to each other. So we can say it follows that G star x is equal to G star x hat. And now this should look familiar from our previous theorem. We know that we can cancel on the left. So by theorem 4.1, it was the left cancellation, so it's part A, 4.1a, we conclude that x equals x hat, right? So there's exactly one element that we can substitute right here to solve that equation. Part B is similar, right? So you should work through it just to practice the steps here. So leave it as an exercise. So part B is similar. Okay, so now there's an important consequence from our theorem. I want to put a star here, so you should put a little mark here. So an important consequence of theorem 4.2 goes like this. The elements in any given row of the Cayley table of a group are distinct and every element of G appears in that row. So this tells you something about the nature of a Cayley table. And this is also true for columns, so let's say ditto for each column. So here's the idea, right? You've got some Cayley table, right? So it corresponds to some group here. All right, so you've got the elements G1, G2, dot, 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 down to Gn. You've got G1, G2, dot, 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 Gn. And so if you focus on, let's say, the ith row, so here's G sub I, what our theorem says is that in this particular row, you are going to see every single element of G appear exactly once. So in this row, every element of G will appear exactly once. And that's a direct consequence of this right here. So for example, what if I had, so this would be like a Gi star G2 right here, and a Gi star G, well, whatever, G sub J right there. So what would that tell us when we have this? Could these two elements be equal? Well, it would only be true by cancellation. It would be true only if G2 is equal to Gj, but they're not. They're distinct elements. So every element will appear, and they will appear exactly one time. You won't see repeats. You're going to need this for one of your homework problems on homework number 1. Okay, this next theorem will kind of, I guess, I don't know, it'll clear up some ambiguity that I've had to carry through ever since we introduced groups. Let's let G be a group with operation star. There's going to be two parts to this theorem, and here's what, if you think back to any time that I've referred to an identity of a group, notice, unless I screwed up, every once in a while I might slip, but throughout I've said that there is an identity, leaving open the possibility that there's more than one identity. This theorem is going to tell us, nope, there's exactly one identity in a group. That's part A. And then part B is going to tell us, another thing you might notice, when I talk about an element, I talk about an element of the inverse. An inverse of the element. What we'll discover in this theorem is that there's exactly one inverse. So each time you have an element in a group, there will be exactly one. So that means that from now on, we'll be able to say the identity of the group, and I'll be able to say the inverse of the element. So that's exciting, right? So part A. Then, okay, there is a unique element little e such that for each little g in G, G star E equals G equals E star G, right? So there's exactly one element E. Part B, for each little g in capital G, there exists a unique G prime in G such that G star G prime equals E equals G prime star G. All right, so identity is unique, inverse is unique. And so let's prove each of these. There shouldn't be any surprises as we go through this proof here, so let's see. So for part A, now remember, we're in a group, so we know that there's at least one. So all we're doing now is we're going to prove the uniqueness. Suppose there's two things that serve as an identity. So suppose there exists an E and an E hat in capital G such that G star E equals G equals E star G, and G star E hat equals G equals E hat star G. Now, what does that tell us? Well, let's just focus on that portion right there. Right? Then we have G star E equals G star E hat. Right? So what do I do? Both G star E equals G and G star E hat equals G. So I can set those two equal to each other. And then what does that mean? Well, now we can apply cancellation. Left cancellation will give us what we need. So by you can list the theorem, or you can just say the property. So I'm just going to say by left cancellation, even though I don't know how to spell it. Cancellation. We have E equals E hat, so that takes care of the uniqueness portion in part A. Now for part B, so let's fix a little g in capital G. Suppose there exists, let's see, I was using a prime, I guess, so let's say there exists a G prime and a G hat in capital G, such that G star G prime equals E, which equals, I think hopefully you can see what's going to happen here, equals G star, or look, G prime star G, and and G star G hat equals E equals G hat star G. So once again, we can look at that portion of the equations right there, and so we can say then G star G prime equals G star G hat. Applying cancellation, so by left cancellation, no, double L this time. By left cancellation, G prime equals G hat. Okay, so that takes care of the uniqueness for inverses. So from now on, and I guess there, let me write my little box. So we finished our proof. From now on, we can say the words the identity and the inverse of G. So now we can say the identity and the inverse of little g. Okay, so that clears up that little ambiguity, right? There is only one inverse for each element, and there's only one identity for the group. Oh, yeah, okay. As a quick corollary, so this is going to be corollary 4.4? Yeah, 4.4. Let G be a group with operation star. For any little g and little h in capital G, if you want to compute the inverse of G star H, we now know exactly who it is. It's equal to H, the inverse of H star inverse of G. So what do? Reverse the order and invert each of the elements. Now, how do we prove this? Well, in our previous theorem, we showed that inverses are unique. So as soon as you find an element that behaves as an inverse, it has to be the inverse, right? So what do I do? Okay, what does that mean? Well, I go like this. So observe that okay, so now I'm going to have G star H star H prime star G. That's equal to G star, so I'm going to use the associativity property now, parentheses in the middle, H star H star H prime star G. Sorry, I need a prime right there and a prime right there. Now, in the middle, oops, and I put a star there. Sorry, that's supposed to be a prime right there also. In the middle, what we have is G star E star G prime. And now, and I can put the parentheses in either side. Let's say I put them like that. Now we know that G star E is equal to G. So this is a G star G prime. And then we know that that's equal to E. Similar computation, so similarly, H prime star G prime star G star H equals the identity. So what have we done? We've shown that this element right here behaves like an identity, right? When you do the multiplication on either side, here we get the identity, here we get the identity. If it behaves like an inverse, it has to be an inverse. In fact, the inverse. So now let's just say it. So apply theorem 4.3b, which says if you behave, is it part B? Yeah. If you behave like an inverse, then you are an inverse. Okay, so it's time to grow up. That's not the right word. It's time to get a little more advanced. And here's the analogy that I want to use. When you were in, I don't know, your younger days of, I guess, elementary school, when you talked about multiplication, you did something like this. 3 times 2. You used a special symbol, right? But then at some point, all right, and you would even do like 3 times x, even though, when you first learned it. And then maybe used a dot instead, right? At some point, because you started using x's, used a dot. But at some point, you said, you know what? We're just going to accept that when we write 3x, what we mean is 3 times x. We're going to do the same thing in groups. So this is sort of more advanced notation, but this is the standard notation that's used in groups. You don't use a star unless you absolutely need some symbol, right? Most of the time, what you do is use juxtaposition to indicate multiplication. So if G is a group, we already know there's some operation there. As soon as you have a group, there has to be an operation. And we have little g and little h in capital G. We use, so if G is a group, we will use multiplicative notation. In place of the symbol star, right? So, so multiplicative notation, that is juxtaposition of elements. Yeah, multiplicative notation of elements to denote the application of the operation. So that is we write GH rather than G star H. So we're just going to drop the star thing. So from now on, I'll just say, let G be a group. And it's understood. There's an operation, and when we want to indicate that we're applying the operation, we will use juxtaposition. I'll just write GH. That means G times H. In particular, when we're working with groups, the operation we want to view as a generalization of the notion of multiplication, right? And so, well, yeah, there is one exception. So, the exception, when G is abelian, that's when we're going to think of it as addition. So when G is abelian, not always, but oftentimes, let's say we will sometimes use additive notation. In other words, I'll write G plus H. Right, rather, but G star H is gone. So in most cases, if we don't have any special information about the group, if we just say let G be a group, and we haven't been specific and said our group is commutative, and we just say let's look at a group G, we will then default to multiplicative notation, which means that when we write this, we will think of the operation as a generalization of multiplication. We'll write GH, and I will say G times H. In certain special cases, when we happen to know that the group is abelian, then we will default to additive notation. I'll write g plus h, and I'll say g plus h. Okay, so now we've been using this symbol prime to indicate the inverse. So now we can get a little better about that. So in multiplicative notation, we'll write g to the minus 1. So this is the inverse of little g, right? That's the standard thing you do when you're working with an inverse, right? We often will think reciprocal, but now we'll just use inverse. So g raised to the minus 1, that is the symbol we will use rather than g prime. That's the symbol that we'll use for the inverse. In additive notation, minus g is the inverse of little g. So you'll just have to understand what's going on oftentimes from context, right? I mean, if you see let g be an abelian group, then more than likely I will write g plus h, and in that case then the inverse will be written with a minus g. Otherwise, I'm going to use juxtaposition, and that will be the symbol that I use for the inverse. Yeah, let's do a little bit more. How much time we got here? Oh, we're not too bad. Yeah, so let's let me just finish off with a little bit more terminology. So really continuing on in our notation now. So if we have a natural number n, then g raised to the nth power will mean exactly what you think it means. G, 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 dot, 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 g, n factors here. And if I write n times g, that means g plus dot, 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 plus g, right, n terms. So we will use this in the multiplicative setting, and we'll use this in the additive setting. All right, so it's just shorthand, g raised to the nth power. That's just shorthand for saying g times g, n times. Oh, of course, g to the 0, so we define g to the 0 to be the identity. And then, of course, we want to make this sort of consistent with how we usually think of exponents. So we'll say also g to the minus n. That means g inverse, dot, 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 g inverse. So there would be n factors. And of course, then, oh, and then for the additive, so this is multiplicative. And then for the additive, we would have minus ng. That means negative g plus dot, 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 plus negative g. And that would be n terms there. Hopefully you can see this. Yeah, that's still in the shot. This is the additive notation. So there's nothing exciting going on here. It's just notation that is consistent with the way we do our arithmetic when we're working with exponents here and when we're working with powers, or multiplication, I guess I should say. And with these rules then, the standard, or with these definitions, the standard rules of exponents now hold. So, so now, the standard rules for exponents hold. So what does that mean? It means that g to the m times g to the n equals g to the m plus n. Here's a couple things. Now, we won't do this right away, but here's a couple of sort of standard things. So when using multiplicative notation, it's actually typical to use the number 1 in place of the identity. So we'll just say 1 is often used in place of E. So it doesn't mean the number 1, it's a symbol standing for the identity of the multiplicative group G. And same thing, so now when using additive notation, 0 is often used in place of E. So when we get more advanced, we might start using that. But for now, I'll just use E for the identity no matter where we are. All right, so anytime when we're working in the abstract, if I am working with a group, whether it's abelian or not, I'll use the symbol E to stand for the identity. Let's end with one last thing here. In fact, this is the end of chapter 4, so let's let G be a group. The order of G is the cardinality of G viewed as a set. I mean, yeah. So remember, when we have a set, we talk about the cardinality. When we're working with a group G, we will say the order of G is the cardinality of the underlying set G, and it's denoted with absolute value bars around G, right? So absolute value bars around G. That's one of the standard ways of indicating cardinality of a set, and now we're going to use that as the order of a group also. So absolute value bars around a group just means tell us what the cardinality is. So for example, the order of Z6 is 6, right? Remember Z6, that is the set 0, 1, 2, 3, 4, and 5 under the operation of addition mod 6, right? Well, there's 6 elements there. The order of the group of integers, remember that's under the operation of addition, right? Well, that's an infinite set, right? So the order is infinity. And we will, I don't know that we'll ever really have, we might every once in a while have occasion to need to talk about whether it's countable or uncountable, right? We know that Z is a countable set. But unless we absolutely need to specify, we just use the symbol infinity to indicate that it's an infinite group. Okay, so that's a good place to stop. We'll start a new chapter on the next lecture. Okay, see ya.